Welcome everybody, I'm Benoît Legat, PhD student at UCL with Professor Youngers and Professor Parillo. I will present you a joint work with Chris, Robin, Joey and Amelia on sum of squares optimization in Julia. We will start by defining what we mean by sum of squares. Given a quadratic form, so a polynomial with only quadratic monomials, there exists a unique matrix Q such that x transpose qx is equal to the polynomial. And we know, even almost by definition, that this matrix is positive semi-definite if and only if the polynomial is non-negative for x. But the advantage of the matrix is that if it is positive semi-definite, then it has a Cholesky decomposition, and from this decomposition we can find a sum of square decomposition for a polynomial. And this decomposition makes it obvious that this polynomial is non-negative. The question is, can we generalize this for other polynomials than quadratic forms? So for example, for this polynomial, can we find a matrix Q such that x transpose qx is equal to it? First, we notice that in x, we no longer only have variables, but we also need to put monomials in it. Second, we need to drop the fact that Q will always be unique. And third, we no longer have the implication that if P is non-negative, then there exists a Q satisfying this equality and such that Q is positive semi-definite. However, we still have that if we find a Q that is positive semi-definite, we can compute the Cholesky decomposition and then find a sum of square decomposition of the polynomials, which is a certificate that this polynomial is non-negative. It turns out that the search for such positive semi-definite matrix Q satisfying these constraints is a semi-definite program. Indeed, the constraint is a linear constraint between the coefficient of the polynomial and the entries of the matrix. So the search for a sum of square certificate of the non-negativity of the polynomial can be done efficiently. In fact, determining whether a polynomial is non-negative or not isn't hard. In fact, Hilbert has identified exactly the only 3 cases in which case every non-negative polynomial is a sum of square. In every other case, there is at least one polynomial that is not a sum of square. However, we had to wait until 1967 for Motzkin to give the first explicit example of a polynomial that is not a sum of squares. It is easy to show that this polynomial is non-negative because it's the arithmetic geometric mean. However, it is not a sum of square. We'll see later that there is also an easy sum of square proof of its non-negativity, but it's not a sum of squares. We now define the sum of square cone. You all know very well the non-negative orthogonal used in linear programming and the semi-definite cone used in semi-definite programming, which is a set of all semi-definite matrices among symmetric matrices with this square product. The sum of square cone is the set of all sum of square polynomials of n variables and up to degree 2d. It is proper, and if we consider the dual space to be the set of measure, and the scalar product of a measure and a polynomial to be this integral, then its dual is the so-called cone of pseudo-measure. A pseudo-measure is a measure that is only required to have a scalar product with every sum of square polynomials to be non-negative, while a normal measure should have a scalar product with any non-negative function to be non-negative. So the cone of pseudo-measure is a superset of the set of measures. Now, what is sum of square programming? It is well known that semi-definite programming is a generalization of linear programming. Indeed, if we consider those matrices, what AI is the I colon of A, then those two programs are equivalent. In sum of square programming, we search for some sum of square polynomial P, such that its integral with some mu I should be bi, and we minimize the integral with mu. In the dual, we have that the sum of the mu I multiplied by some scalar yi should be smaller in the sense of the cone of pseudo measure than some nu. We can see that this is a generalization of semi-definite programming, because if we take mu that have the same second order moments are the entries of A, and nu that are the second order moments which is equal to the entries of C, and P to be this quadratic forms, then the two programs are equivalent. There used to be 3 separate implementations of sum-of-square programming in Julia, but we decided to join our forces into one framework. There is the multivariate polynomials, which implement many common operations between multivariate polynomials, and 2 implementations of them. Those 2 used to be only one package, but then Robin found a very efficient way to represent polynomials. Comparing to dynamic polynomials, it stores a lot more information from the field to the type, and so a lot of the computation effort is moved from the runtime to compile time and is done then only once. And so it's a lot faster. Then there is a sum-of-square package which implements the reformulation of sum-of-square into SDP, and the polyjump package which extends jump to polynomial optimization. When you use multivariate polynomials, you need to choose one of the 2 implementations. Then you will first need to define the variables you will use. So you can either define a scalar variable, for example here y, or a vector variables with a similar syntax are the jump syntax for creating variables. Then you can either build a polynomial from scratch. For example, this would be the mode scheme polynomials if x is a scalar variable and y2. But one other very important operation that we will use is to build a vector of all monomials of some degree. So this gives all the monomials of x1 and x2 that have exactly degree 2, and this gives all the monomials that have degree between 0 and 2. Polyjump tries to extend jump with a familiar syntax for creating polynomial constraints and polynomial variables. Here, we are searching for a value for a such that this polynomial is non-negative. It is very important to distinguish decision variables of jump and polynomial variables. Here, a is a decision variable and x and y are polynomial variable created using polyvar. So we are searching for a value for a such that this expression is non-negative for every value of x and y. We are not searching for x and y here. We can also create a polynomial variable. So here we're trying to create a polynomial variable p of 2 variables and degree up to 2, such that it is strictly positive and its product with the Motzkin polynomial is non-negative. What we are trying to do is we are trying to build a sum-of-square proof that the Motzkin polynomial is non-negative. As I told you earlier, this is possible. In fact, this problem is feasible and we can find this value for p. If we extract the slack from this constraint and these constraints, we can get its sum-of-square decomposition. And with this 3 sum-of-square decomposition, we have a proof that the Motzkin polynomial is non-negative. Indeed, if its product with a strictly positive polynomial is non-negative, then the Motzkin polynomial must be non-negative. Polyjump is just a modeling language for polynomial optimization. It does not explain how to reformulate the problem into something that can be solved by the solver. You need a polymodule for that. The only one that exists for now is sum of squares, so you need to use this line to tell it to use sum of squares. There is an equivalent shortest form, which is this one, defined in sum of squares. The only use of the first one, if in case you use a jump extension that use something different that model here, in which case you cannot do that, then you will need to use this two-line version and add this separately. Then, sum of squares, we use sum of square approximation to reformulate the polynomial optimization problem into an SDP that can be solved by a semi-definite solver, such as Mosaic SDP and so on. Of course, if you use only the weaker condition DSOS or SDSOS, then you only need an LP or SOCP solver to solve the problem. As I said earlier, in a polynomial constraint, we are trying to prove that this constraint is satisfied for all value of x and y. However, in some cases, we only want to constrain that it's satisfied for the value of x and y satisfying some equalities or some inequalities. In other words, we are only trying to show that some polynomial is non-negative on some set. Those sets can easily be handled if they are algebraic sets or basic semi-algebraic sets. So the finite union of algebraic equalities or the finite union of algebraic inequalities and equalities. The equalities are handled quite differently than the inequalities because we can use Grobner basis to do the division and stuff like that in case the coefficients here are only constant and does not depend of the jump decision variables. So we distinguish those two cases. And in this case, we'll first handle the inequalities and then those equalities will be handled with Grobner basis, as with this case. So for example here, we want to constrain this inequality to be satisfied, but only on the unit circle. So we only need to prove that 10 minus s squared minus y is non-negative on the unit circle. So we only need to find a sum of squares that is equal to 10 minus s squared minus y on the unit circle. Here you see the polynomial only agree here on the unit circle. We have seen that we can create one polynomial variable using this syntax. Here x is the vector of monomial of this polynomial. Internally, we create one jump variable per each coefficient of each monomial. However, if you know that you want p to be sum of square, you could say variable p poly and then constraint p sum of square, but it's more efficient to directly declare it as sum of square. So what you do is this, p SOS poly x, where x here is not the vector of monomials of p, but the vector of monomials in this form. And we directly constrain q to be positive semi-definite, and we create one jump variable per entry of q. Of course, not one per entry because it's metric. You could also do DSOS or SDSOS, where instead we constrain q to be diagonally dominant with only require linear programming, or scaled diagonally dominant with only require second order cone programming. This is a stronger condition, but it's more efficient to solve because it's linear programming. There is the same thing for constraints. Here this is equivalent to writing p larger than 0, this constraint p to be sum of square, this constraint p to be diagonally sum of square, so this is stronger condition, but simpler to solve. And here we constrain p to be scaled diagonally dominant. Sometimes we have a polynomial matrix, so a matrix for which every entry is a polynomial, and we want to satisfy that this matrix is positive semi-definite for every value of the polynomial variables. A certificate for this can be given if we prove that this matrix is a sum of square matrix. This can be shown in two equivalent ways. Either we give Cholesky decomposition of this matrix, or we create new variables y, and we compute the polynomial y transpose py, and we find a sum of square decomposition for this new polynomial. Adding this constraint is polygem is very similar to how you would ask a matrix to be positive semi-definite. You just write the matrix for which entries can be polynomial, for which the coefficient can be a fine expression of jump variables, while if you constrain a classical matrix in jump to be positive semi-definite, you just have every entry to be in jump variables. Here you can have polynomial for which the coefficient are jump variables. It can be useful when you want to constrain a polynomial to be convex. Of course, if the Hessian of the polynomial is positive semi-definite for every value of x, then p of x is convex. Here you can compute the Hessian with this function of multivariate polynomials, and then you just constrain it to be semi-definite for every value of x, which will be translated to the sum of squares matrix constraints in sum of squares. When we constrain p to be a sum of square, we look for a matrix Q positive semi-definite such that x transpose Qx is equal to p. But how do we know the monomials that we put in X? Suppose, for example, that we have this P. What we do is we compute the Newton polytope of P which is the convex hull of those green points. The green points are the exponents of the monomial. So 2, 2 is here, 2, 2. 4, 0 is here. This is 2, 1, this one, and so on. Then we know that the monomials that we put in X are the monomials corresponding to the points in this red set, which is the Newton polytope divided by 2. So we have only these 3 points. Here we say that if you multiply any of these 3 monomials between them, we can have any monomials in this triangle. So we see we can never have this one. So actually we know only by computing the Newton polytope that this is not a sum of squares. So in practice, we get these points, then we compute the facets of this polytope to have an oracle to decide whether a polynomial is in this red polytope or not. However, computing the facets of a polytope in n dimension from its vertices may be computationally extensive. So what we do by default is we compute this cheap outer approximation of the Newton polytope and use it. For example, here we have one monomial that we know do not need to be considered if you compute the exact Newton polytope, but since we have an outer approximation, we still use it. If you want to compute the exact Newton polytope, you can ask it. You just give a polyhedral computation library, here CDD, where you have the choice between floating point arithmetic and exact arithmetic. In some cases, there is a special structure in P. Here, if we compute, if H is a polynomial matrix and we compute Y transpose HX, Y, we know that for each monomial, the sum of the degree of the Y variables would always be 2. And so we know that we can compute the Newton polytope exactly by taking the Cartesian product of the Newton polytope for the Y variables and the Newton polytope for the X variables. And also we know that the Newton polytope for the Y variables can be computed exactly by this outer approximation, in fact, because you have all the monomials of degree 2. We now present 2 applications. Suppose first that you want to minimize a polynomial on some basic semi-algebraic set S. Suppose you want to minimize this polynomial in the set so that x and y are non-negative and x plus y is larger than 1. Write this sum of square program where you say I want a jump variable LB, the lower bound. I want to maximize this lower bound such that it is smaller than the polynomial in this set S. If you do this, you will get a lower bound, maybe not the exact minimum of P, because P minus LB might be non-negative but not a sum of squares. As we did with the Motzkin polynomial, you can pre-multiply this by a polynomial to get a better lower bound. And the pre-multiplier, if you consider higher and higher degree, you will get a better lower bound. So you have an hierarchy of programs, and if you climb up this hierarchy, you will get a better and better lower bound. At some point, you might get the exact lower bound. How do you detect it? You take the constraints and you ask get dual on these constraints, and you try to see if it's atomic. An atomic measure is a measure that is the sum of some Diracs at some discrete points. If it is, then the atoms are the minimizer of this function on S, and LB, the lower bound, is the exact minimum. At the second application, we will see how to find a Lyapunov function for a system. Here, as an example, we consider a switch system with 2 dynamics. So the discrete system can either use the dynamic A1 or A2 at each time. And we want to find a Lyapunov that works for both dynamic, because it will show that whatever is the switching between these 2 dynamics, the system will always be stable. So we want to find a Lyapunov function, which is a polynomial variable that has monomials that are all the monomials of degree 2D. We consider only those monomials and not the monomials of degree 2D minus 1 and so on, so that we have a homogeneous polynomial, and that makes sense because the system is homogeneous. We want it to be strictly positive, And we also want v to be a Legat function for both dynamics. This is the nice syntax to do a substitution of the variables x in the polynomials by ai stamp x. So this. As with the previous case, the dual will be helpful. Here, if this is infeasible, if you cannot find a Legat function, by taking the dual variables here and trying to check if it's atomic. If they are atomic, then you can extract from them a periodic trajectory that is unstable. So from this, you can see what is the switching sequence that makes this seem unstable. And in fact, even if they are not atomic, you can still recover an unstable trajectory sometimes. I invite you to check the switch system package for more details about this. We end the presentation with a list of future work. So it is a non-exhaustive list. If you want something else to be implemented, please tell us. First, symmetry reduction. If a problem is symmetric and it's a convex problem, which is our case, we know that at least one optimal solution is symmetric, so we can significantly reduce the problem. Then in X transpose QS, in X we have only considered monomials, but it can be actually any polynomial basis. Some bases can give better numerical behaviors. Then for dealing with polynomial constraint in algebraic sets, we have seen that we can compute Grobner bases, but then sometimes it's computationally intensive. So of course, in some cases, we know how to divide by the algebraic set, so we can do something specific for them. And also sometimes we can do sampling instead. Then we have seen that we can have polynomial variables and polynomial constraints and measure at the dual, but sometimes you also want to have measure variables and measure constraints and model with them directly. For example, we have seen that the coefficient of the polynomials are a fine expression of jump decision variable, but sometimes you want the algebraic constraints to be satisfied where the variables are the decision variables. For example, you have a vector of fine expression of decision variable and you want it to be to belongs to some algebraic set, so to satisfy some algebraic constraints. And this can be done using moment relaxation. Then in quantum theory and quantum information theory, you often have non-commutative variables and also emission variables, so x transpose equal x, or x transpose x equals 0, or x squared equal x. Non-commutative has already been done, but then this one needs to be tackled still. And then we have seen that we sometimes want to have an hierarchy of programs, and when you climb up the hierarchy, you are more and more precise, but it's more and more computationally intensive. And we want to have a nice syntax for that. That's it. Thanks for listening.